Tonight, we're going to follow a single spacecraft into the future, Voyager 1. Right now, it's drifting through interstellar space farther from home than anything humanity has ever built. Its power fades a little more every year, and within the next decade it will fall silent forever. But the signal dying has nothing to do with the machine stopping. 1 trillion years from now, the sun will have gone cold. Every star you can see right now will have burned through its fuel and gone dark. The galaxy itself will have changed into something almost unrecognizable. And Voyager 1 will still be out there, still moving, still carrying its golden record through a universe that will have long since forgotten it ever existed. By the end of tonight, you're going to see exactly what that universe looks like, where this machine actually ends up inside it, and why something built to last 5 years is on track to outlast nearly everything. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Start with what Voyager 1 actually is right now in the present. It was launched on September 5th, 1977 from Cape Canaveral, Florida. It carries a golden record, sounds of Earth, whale songs, greetings in dozens of languages, music from different cultures, a message in a bottle thrown into an ocean with no shore. It was designed to study Jupiter and Saturn. It did that job and then it kept going. In August of 2012, it crossed the helopause, the boundary where the sun's solar wind gives way to the thin plasma of interstellar space. It became the first human-made object to leave the solar system's protective bubble. Today, it's more than 15 billion miles from Earth. It's moving at about 38,000 km relative to the Sun. Its transmitter still works. Its instruments still send back data fainter and fainter, arriving on Earth after a radio delay of more than 23 hours one way. But its power is fading. The radioisotope thermoelectric generator that keeps it alive loses about 4 watts of output every year. And engineers expect the last instruments to fall silent sometime in the early 2030s. After that, Voyager 1 won't send us anything else. Not ever again. It won't be broken in any conventional sense. It will simply run out of the power needed to speak. And this is where most stories about Voyager end. The silence. The idea of a dead spacecraft drifting forever. But that's not actually the end of anything. That's the beginning of the part almost nobody talks about because Voyager 1 won't stop moving. It won't corrode because there's no oxygen or moisture in deep space to rust it. It won't burn up because there's no atmosphere to create friction. It won't be struck by debris in any meaningful sense because interstellar space is close to perfectly empty. There is nothing out there to stop it, slow it, or destroy it. So, it keeps going forever unless something extraordinarily unlikely happens to it, and that single fact is the seed of everything we're about to explore. A silent metal object, unpowered, unguided, continuing to travel through the galaxy for longer than anything else our species has ever built. Longer than our species itself. Longer than the sun. Let's put the near future in perspective first, because even the soon timeline is strange enough on its own. In about 40,000 years, Voyager 1 will pass within roughly 1.6 light-years of a star called Gliese 445, a small red dwarf in the constellation Camelopardalis. It won't visit it in any meaningful sense. It will simply drift past at a distance greater than the gap between our own sun and its nearest neighbour. No flyby. No close encounter, just 2 objects sharing a small patch of the galaxy for a cosmic instant before separating again. 40,000 years sounds enormous, and it is by any human measure. But we need to hold on to that number because everything that follows is going to make 40,000 years look like nothing. At all. Voyager isn't bound to our solar system anymore. It's bound to the galaxy. It's now essentially its own tiny planet orbiting the centre of the Milky Way the same way Earth orbits the Sun, just on a much larger, much slower loop. Our Sun takes about 230 million years to complete one orbit around the galactic centre. Voyager, moving on its own independent path, will do something similar, tracing loops around the galaxy for as long as the galaxy exists, in a form that can hold it, and that's the real subject of tonight. Not years, not thousands of years, not even millions. We're going all the way out to 1 trillion years, and to understand what that means for Voyager, we first need to understand what happens to everything else around it. The first major event on our timeline isn't really about Voyager at all. It's about home. In roughly 5 billion years, our sun will run out of hydrogen fuel in its core. It will begin fusing helium instead, and in the process it will swell into a red giant, its outer layers expanding outward, engulfing Mercury, then Venus, and quite possibly reaching all the way to Earth's orbit. By this point, Earth will almost certainly be uninhabitable if it exists as a rocky body at all. The oceans will have boiled away long before that. The atmosphere stripped, the surface scorched. Voyager by then will be so far from the solar system that none of this touches it directly. It left the gravitational influence of the sun behind a long, long time ago. It won't feel the sun's death as heat or light. It's simply too far away, adrift in interstellar space, indifferent to what happens back at the point where it was built. The sun will eventually shed its outer layers entirely, forming a glowing shell of gas called a planetary nebula, while its core collapses into a white dwarf, a dense ember about the size of Earth that will cool for trillions of years. Voyager will still be out there when this happens. A tiny relic from a civilization that no longer has a home star to return to. Now, stretch the timeline further into the trillions and something even stranger takes over. Star formation itself is a temporary phase in the life of the universe. Stars form from clouds of hydrogen and helium gas. Every time a star is born, some of that raw material gets locked away, either burned in fusion or scattered as heavier elements that don't easily form new stars as efficiently. Over time, the galaxy's supply of star-forming gas runs low. Astronomers estimate that the last stars capable of forming will appear somewhere between 1 trillion and 100 trillion years from now with red dwarfs, the smallest and most fuel-efficient stars being the last ones lit. Red dwarfs burn their fuel so slowly that some of them forming today could still be shining 1 trillion years into the future. That means when we ask where Voyager will be in 1 trillion years, we're not asking about some distant dead husk of a galaxy. We're asking about a period when the last generation of stars may still be flickering in the dark. Tiny, dim red embers scattered across a much emptier sky than the one we know. By this point, the Milky Way as a distinct galaxy won't exist anymore, at least not in the shape we recognize. Here's where the story of Voyager intersects with the story of an entire galaxy colliding with another. Our galaxy, the Milky Way, and the nearby Andromeda galaxy are moving toward each other, closing the gap at roughly 250,000 Teraborceslius p.m. Current estimates suggest the two galaxies will begin merging music in about 4.5 billion years, with the process fully completing and settling into a single elliptical galaxy, sometimes nicknamed Milomeda, over the following few billion years after that. During this merger, individual stars almost never collide with each other directly. Space between stars, even within a galaxy, is so vast that the chance of two stars actually striking one another is close to zero. Instead, gravity reshuffles everything. Stars get flung into new orbits, some ejected entirely. From the merged galaxy, sent drifting alone into intergalactic space. Voyager, by this point already ancient beyond any human frame of reference, will be caught up in this reshuffling too, not as a star but as a tiny piece of debris following whatever gravitational path the collision assigns to the region of space it happens to occupy. There's a real possibility, though not a certainty, that Voyager could end up ejected from the merged galaxy entirely, flung out into the vast emptiness between galaxies. A single, silent object drifting through a void so profound that the nearest galaxy might be millions of light years away in any direction. Or it could remain bound to Milka, tracing enormous loops through the merged galaxy for the rest of its unimaginably long existence. Either outcome is possible, and honestly, we can't say for certain which one it will be, because we're talking about gravitational interactions over timescales so long that even our best simulations carry enormous uncertainty. What we can say is that Voyager will survive the merger. There's essentially nothing in intergalactic space capable of destroying it. Consider what the sky itself will look like by the time we reach the trillion-year mark. Because this is where things start to feel genuinely unsettling. The universe is expanding, and that expansion is accelerating, driven by whatever we're currently calling dark energy. Right now, we can see galaxies billions of light years away, their light having travelled across almost the entire history of the universe to reach us. But as the universe keeps expanding, more and more distant galaxies will cross a boundary called the cosmological horizon, a point beyond which their light can never reach us again, because the space between us and them is stretching faster than light can cross it. Astronomers estimate that within about 100 billion years, nearly every galaxy outside our own local group will have become permanently invisible, their light redshifted into nothingness, their existence erased from what any observer inside Milky could ever detect again. By the time we reach 1 trillion years, this process will be long finished. The night sky, if there's anything left nearby to look up from, won't show the countless galaxies we see today. It will show a single merged galactic structure, our own, and beyond it, nothing. Total darkness. No other galaxies, no cosmic web, no distant light, just isolation on a scale that dwarfs anything we currently experience. Voyager drifting somewhere in or around what remains of the Milky Way, and Andromeda's merger will exist in that darkness, a machine built by a species that once looked up and saw a sky full of galaxies, now travelling through an emptiness where none of that remains visible at all. There's also the matter of the stars that are still around at that point, and honestly, there won't be many left in a form we'd recognise. By 1 trillion years, most sun-like stars across the universe will have exhausted their fuel and collapsed into white dwarfs, dense Earth-sized embers, slowly, radiating away their leftover heat into space. These white dwarfs cool incredibly slowly. It's estimated to take on the order of quadrillions of years for a white dwarf to cool all the way down to what's called a black dwarf, a cold, dark, inert stellar remnant that no longer glows at all. At 1 trillion years, most white dwarfs will still be faintly warm, glowing a dull, deep red, nothing like the bright yellow-white light our sun produces today. The red dwarfs, still burning at this point, will be dimmer still, sipping their hydrogen so slowly that they're expected to remain lit for tens of trillions of years before finally exhausting their fuel too. If Voyager happened to drift near one of these dying embers, its instruments, long since silent, wouldn't register anything. There would be no one aboard to look, no camera actively capturing images, no sensor actively reporting data. It would simply pass by a cold piece of metal gliding past a cooling star in a universe that has almost entirely gone quiet. Now, here's a question worth sitting with for a moment. Would Voyager even still be recognizable as Voyager after 1 trillion years? The honest answer is probably yes. Structurally, though almost certainly not electronically. There's no atmosphere in deep space to erode it, no water to rust its metal frame, no biological processes to break it down. Micrometeorite impacts are possible, but statistically rare over any given stretch of time, because interstellar space is staggeringly empty. Even so, over spans of time, this extreme small effects add up. Cosmic rays, high-energy particles from distant sources will continually strike Voyager's surface, slowly degrading its materials at the atomic level over unimaginable stretches of time. The golden record, plated in gold and designed specifically to resist this kind of degradation, was built with exactly this scenario in mind. Carl Sagan and the team behind it wanted something that could survive not for centuries but for a truly cosmic span of time, on the chance that someday another mind might come across it. It's reasonable to think that after 1 trillion years, Voyager's basic shape, its antenna, its instrument booms, its main body, would still exist in some form, pitted and worn by radiation, but not vaporized, not destroyed, simply old, beyond any concept of old that makes intuitive sense. So where physically would it actually be? This is the part where we have to be honest about the limits of prediction. Voyager's exact position after 1 trillion years depends on an almost incomprehensible chain of gravitational interactions, the merger with Andromeda, possible ejections and recaptures during that merger, further mergers with smaller nearby galaxies that are expected to be absorbed into Milky over the following tens of billions of years, and the slow chaotic churn of orbits within whatever galactic structure eventually settles into place. We can't give you exact coordinates because nobody can. The uncertainty compounds too much over that length of time, but we can describe the range of likely outcomes because gravitational physics doesn't change even if we can't track every variable perfectly across 1 trillion years. One possibility places Voyager still orbiting within the combined body of the Milky Way and Andromeda, tracing an enormous slow loop through the merged galaxy's outer regions. One full orbit taking hundreds of millions of years or more, an orbit so vast and so slow that Voyager would complete only a handful of them across the entire span from now until the trillion-year mark. Another possibility, and a genuinely plausible one, is that gravitational interactions during the galactic merger flung Voyager out entirely, sending it drifting into intergalactic space, no longer orbiting anything at all, simply moving in a straight line or as close to straight as gravity from extremely distant structures allows, through a void so empty that it might not encounter another significant gravitational body for the rest of its existence. Either way, Voyager isn't going anywhere in the sense of a destination. There's no arrival waiting for it. There's only continuation. It helps to think about scale for a moment, because 1 trillion years is not simply a big version of 1 million years. It's a different category of time entirely. The universe itself is currently about 13.8 billion years old. 1 trillion years is more than 70 times the current age of the entire universe. If you compress the full history of the universe from the Big Bang until today into a single day, 1 trillion years would still stretch more than 70. Days beyond that point, everything that has ever happened, every star that has ever formed, every galaxy we've ever observed, every moment of human history fits into a sliver of time so small compared to 1 trillion years that it barely registers as a fraction. And Voyager, this small human-built machine, is expected to simply keep existing, keep moving through nearly the entirety of that unimaginable stretch, not operating, not sending signals, not doing anything in any active sense, just persisting, a fixed physical object, obeying the same laws of motion that took it out of the solar system in the first place, carried along now by gravity on a scale far beyond anything its creators ever imagined when they bolted its instruments together in a clean room in California. There's something worth pausing on here, and it's not really about physics. It's about what Voyager represents right now in this exact moment. Voyager 1 is the farthest reaching physical expression of human curiosity that has ever existed. Every civilization that has come before us built things meant to last. Pyramids, cathedrals, monuments carved into mountainsides. All of them without exception are temporary on a cosmic scale. Wind and rain and time erode stone. Empires fall, languages disappear. But Voyager, sitting in the near-perfect vacuum of interstellar space, protected from nearly everything that destroys objects on Earth, is arguably the most durable thing humanity has ever built, precisely because it was sent somewhere. That nothing much happens. By the time it reaches the 1 trillion year mark, if it does so intact, It will have outlasted our sun by hundreds of billions of years. It will have outlasted our species almost certainly, along with every language we've ever spoken, every structure we've ever built, every memory we've ever recorded, except for the small collection of sounds and images etched onto that golden record, which may by then be the only remaining evidence that humanity existed at all. It's worth being clear about the uncertainties here, because good science means being honest about what we don't know. We don't know for certain that Voyager will avoid a collision over that timescale, though the odds strongly favour it given how empty interstellar and intergalactic space actually are. We don't know exactly where the galactic merger will place it, whether inside the merged galaxy or flung out into the emptiness beyond. We don't know with certainty how radiation damage will affect its structure after such an enormous span of time, only that current physics suggests it should remain largely intact in shape, even if every working part of it has long since gone silent. What we do know with a fairly high degree of confidence is that it will still exist in some recognizable form, still moving, still following the same fundamental laws of gravity and motion that have governed it since the moment it left Earth. There is no plausible mechanism based on everything we currently understand about physics that would erase it entirely before then. So, picture it 1 trillion years from now. The sun that launched it is long gone, its material scattered or locked inside a cooling white dwarf ember. Earth, if any trace of it remains at all, is unrecognizable and possibly no longer exists as a distinct body. The Milky Way and Andromeda merged into a single galaxy so long ago that the event itself is ancient history. Even by the standards of that era, most of the stars capable of shining have already gone dark, the last of the red dwarfs finally sputtering out, leaving behind a galaxy filled mostly with cold black remnants drifting silently through space. The sky, if anyone were there to observe it, shows no other galaxies at all. The entire rest of the universe having drifted beyond the reach of light a long, long time before, and somewhere in that darkness, whether looping slowly through what remains of the merged galaxy or drifting alone through the emptiness beyond it, a small metal spacecraft, its instruments silent, its power gone, its golden record, still faintly, reflecting whatever dim light happens to fall on it, continues on, not moving toward anything, not moving away from anything in any meaningful sense, simply continuing the way it has continued since 1977, obeying the same laws of motion, carrying the same message, indifferent to the almost incomprehensible span of time that separates that moment from this one. It is, in a very real sense, one of the closest things to permanence that our species has ever created, not because we built it to last forever, but because we sent it somewhere that nothing gets in the way. That's the answer. But to really understand how something ends up drifting for 1 trillion years, it helps to look closer at a few of the details sitting underneath everything we've covered so far. Noughts. Start with the power source, because that's the detail that actually decides when Voyager crosses from being an active spacecraft into being a silent drifting artifact. Voyager carries 3 radioisotope thermoelectric generators. Inside each one sits a core of plutonium-238, a man-made isotope that decays steadily, releasing heat that gets converted into electricity by thermal pulls, solid-state devices with no moving parts. This is why Voyager has run for close to 50 years without a single mechanical failure in its power system. There's nothing to break, but there is decay, and decay is relentless. Plutonium-238 has a half-life of about 87.7 years, meaning every 87 years or so, half of what remains simply stops. Producing heat at the previous rate, Voyager loses roughly 4 watts of available power every single year, and engineers have been shutting down instruments, one at a time, to cope. Sometime in the early 2030s, the last instrument will draw more power than the generators can supply, and mission controllers on Earth will lose their final channel of communication with the spacecraft. At that point, Voyager stops being a mission and becomes a monument, an object, not an instrument, a thing moving through space rather than a thing observing space. And this is really the moment where the rest of tonight's story begins. Everything we've described so far happens after that transition music, in the overwhelming majority of Voyager's actual existence, when it's no longer sensing anything or reporting anything at all. Let's look at what actually threatens or doesn't threaten Voyager's physical structure over a stretch of time this long. There's no oxygen in interstellar space to cause rust. There's no moisture to cause corrosion. There's no wind, no rain, no biological organisms of any kind capable of breaking it down. The primary threats over cosmic timescales are cosmic rays, extremely high-energy particles travelling at close to the speed of light, and far more rarely, collisions with dust or debris. When a cosmic ray strikes a solid object, it can knock individual atoms loose, or subtly alter the structure of materials at a microscopic level. Over the span of decades, this effect is negligible. Over the span of 1 trillion years, it adds up, gradually causing microscopic pitting across the surface of the spacecraft. Even so, physicists generally agree this kind of slow atomic level erosion is unlikely to destroy the object entirely because the rate of damage remains extraordinarily slow compared to the sheer amount of solid material making up Voyager's frame. Collisions with dust are a more sudden, if statistically rare, threat, but interstellar space contains so little dust that meaningful collisions remain exceptionally unlikely even across 1 trillion years of continuous travel. The overwhelming likelihood is that Voyager simply keeps drifting, unbothered, its shape degrading slowly at the atomic level, but remaining fundamentally intact and recognizable. The Golden Record shares in this durability. It's made of gold-plated copper, chosen specifically because gold resists corrosion, music, and tarnishing far better than almost any other readily available material. Carl Shawn and the team behind it built it with exactly this kind of timescale in mind. At 1 trillion years, the record should still exist, still legible in principle. A small gold-plated disc carrying music, sounds and images from a civilization that existed for the briefest possible sliver of the universe's total history. Let's put the near future in perspective first, because even the soon timeline is strange enough on its own. In about 40,000 years, Voyager 1 will pass within roughly 1.6 light-years of a star called Gliese 445, a small red dwarf in the constellation Camelopardalis. It won't visit it in any meaningful sense, just drift past at a distance greater than the gap between our own sun and its nearest neighbour, a little further out in about 296,000 years. Voyager is expected to pass within about 4.5 light-years of Sirius, the brightest star in Earth's night sky. Again, no capture, no meaningful interaction. Just two objects briefly occupying the same general region of the galaxy before drifting apart. It's the way ships pass each other on an ocean too large for either of them to notice the other. Even after travelling for hundreds of thousands of years, Voyager isn't really approaching anything in a meaningful sense. It's simply moving through a galaxy so enormous and so empty between its stars that even a close approach by cosmic standards amounts to a gap of trillions of miles. We already talked about what happens to our sun, but it's worth spending a little more time on the rest of the solar system it leaves behind, since Voyager's story doesn't unfold in total isolation from everything it left. Jupiter and Saturn will likely survive the sun's transformation music into a red giant relatively intact, orbiting far enough out that the expanding sun probably won't reach them directly. Some of their icy moons, worlds like Europa and Enceladus, are believed by scientists to hide liquid water oceans beneath their ice. Today, that ice would likely melt or vaporize as the sun's increased output warms the outer solar system for the first time in its entire history. That creates a strange brief window, perhaps a few 100 million years. During it, the outer solar system becomes more hospitable to liquid water than it's ever been. Right around the same time, the inner solar system turns into a scorched wasteland. Eventually, once the sun settles into its white dwarf remnant, the surviving outer planets will keep orbiting that faint ember for a very long time, their orbits gradually destabilizing from the combined gravitational tug of passing stars. Some models suggest that over sufficiently long time scales on the order of many trillions of years, these planets could eventually be stripped away entirely, becoming rogue planets, drifting through the galaxy without any star to call home. Current surveys actually suggest rogue planets, worlds ejected from their birth systems this way, may already outnumber planets still orbiting stars within the galaxy, drifting in permanent darkness and cold. If Voyager is eventually ejected from the merged galaxy we're about to describe, it will on a vastly smaller scale join this same population of homeless wanderers. It would be a tiny artificial object rather than an entire world, but shaped by the exact same gravitational forces. We touched on the Milky Way and Andromeda colliding, but it's worth understanding a bit more of the mechanics since they shape exactly where Voyager ends up. Andromeda is currently approaching us at roughly 250,000 draws, and current projections suggest the two galaxies will make their first close pass in roughly 4.5 billion years. That first pass won't destroy either galaxy outright. Instead, gravity begins pulling long streams of stars and gas out into sweeping arcs, a process astronomers have already observed in other colliding galaxy pairs across the universe. The two galaxies separate again after that first pass, only to be pulled back together for additional closer passes over the following billions of years. They finally settle into a single, elliptical galaxy, sometimes nicknamed Milky, likely within 6 to 7 billion years from now. Both galaxies carry a supermassive black hole at their centre, ours known as Sagittarius A, with a mass equivalent to about 4 million suns. Andromeda's considerably larger at roughly 100 million solar masses. As the merger completes, these two black holes are expected to spiral toward each other over hundreds of millions of years and eventually merge into one. That merger will release a burst of gravitational waves that spread outward at the speed of light, though far too weak by the time they'd reach anything like Voyager to have any physical effect on it at all. There's a detail worth adding to where Voyager physically ends up in all of this. Our solar system currently sits about 26,000 light-year from the centre of the Milky Way, out in one of the galaxy's spiral arms. Objects near a galaxy's outer regions are statistically more likely to be flung outward during a merger simply because they're less tightly bound by gravity than objects closer to the centre. Voyager left the solar system on a trajectory carrying it generally outward relative to the galaxy's structure that may make it even more loosely bound than most stars in our region. By the time the merger's gravitational chaos gets underway, modestly raising the odds, it ends up among the objects ejected from Milky entirely, rather than remaining in orbit within it. It helps to make the sun's fate and the fates we've been describing a little more concrete by naming a few actual stars visible in tonight's sky and tracing what happens to each of them. Betelgeuse, the bright reddish star marking the shoulder of Orion, is already a red supergiant, far more massive than our Sun. It's expected to end its life in a supernova at some point. Astronomically speaking, soon, though soon in this context could mean any time within the next 100,000 years. When it does explode, it will briefly become bright enough to be visible in broad daylight from Earth before fading, and leaving behind either a neutron star or, if it's massive enough, a black hole. Sirius, the same star Voyager will eventually pass at a considerable distance, is a bright sun-like star paired with a smaller white dwarf companion. It's expected to follow a path much like our own Sun, exhausting its hydrogen in a few billion years and eventually settling into its own white dwarf remnant. Proxima Centauri, the nearest star to our Sun and a small red dwarf, is exactly the kind of star expected to still be shining at the 1 trillion-year mark, It patiently burns its fuel at a pace so slow that current estimates give it a total lifespan measured in trillions of years, making it one of the very last active stars anywhere by the time Voyager reaches that distant point in its journey. Not every star gets an ending this quiet, though, and it's worth knowing the wider picture because the galaxy Voyager drifts through won't just be full of dimming embers like our suns. Stars significantly more massive than our sun, roughly 8 times its mass or more, end their lives in a completely different, far more violent way. Their cores collapse in a matter of seconds, triggering a supernova, an explosion that can briefly outshine an entire galaxy before fading. What's left behind depends on how massive the original star was. Sometimes it's a neutron star, an object barely 12 meters across, but containing more mass than our entire sun. And sometimes, for the most massive stars, it's a black hole, a region of space where gravity is so intense that nothing, not even light, can escape once it crosses the event horizon. Nearly all of these massive, rare, fast-burning stars will have already ended this way long before Voyager reaches even a small fraction of its trillion-year journey. Stars that large burn through their fuel in a matter of millions of years, a blink of an eye by comparison to everything else on this timeline. By the time Voyager reaches 1 trillion years, supernova will have become exceptionally rare. What's left instead is a slow accumulation of quiet endings. White, dwarfs cooling, neutron stars spinning silently as their once rapid pulses of radiation gradually slow, and black holes, patient and largely inert, simply sitting wherever they settled, before Andromeda even arrives. The Milky Way has smaller company that's actually expected to show up first. The large and small melanic clouds are 2 smaller companion galaxies, Music, currently orbiting the Milky Way, gravitationally bound to it, much the way a moon orbits a planet, unlike Andromeda, which is still millions of light years away and approaching slowly. The large melanic cloud is close enough, and its orbit unstable enough that current models suggest something surprising. It may actually collide with and merge into the Milky Way within the next 2 to 2.12 billion years, well before the larger, more dramatic Andromeda merger even begins. This smaller merger likely wouldn't be nearly as disruptive to the Milky Way's overall structure, but it would still trigger a wave of new star formation, and the same basics, gravitational reshuffling of stars and orbits, will see play out on a much larger scale later on. By the time Andromeda does arrive, the Milky Way it merges with, it won't be quite the same galaxy we observe today, having already absorbed several smaller companions of its own. Voyager drifting through the outer reaches of the galaxy during this entire span would be indifferent to any of it. It's far too small and far too distant from these events to be meaningfully affected, simply continuing its slow orbit around the Music galactic center, while the galaxy around it steadily grows, merges, and reshapes itself over billions of years. It's worth knowing a little about what Voyager is actually moving through this entire time, since interstellar space isn't a perfect void, just an extraordinarily sparse one. The interstellar medium consists mostly of hydrogen and helium gas left over from the earlier stages of the universe, combined with material expelled by dying stars over billions of years. Tiny grains of dust are scattered incredibly thinly across vast distances too. In the region Voyager currently occupies, the density is estimated at roughly 1 particle per cubic inch. That's an almost unimaginably empty environment compared to the air around you right now, which contains something on the order of 100 quintillion or more air molecules within that same volume of space. This extreme sparseness is precisely why Voyager can travel for such enormous distances, Music, without any meaningful risk of collision. It's also worth knowing what temperature Voyager is actually experiencing out there, since without a sun nearby, deep space isn't simply cold. It's cold in a very specific, well-defined way. Once far enough from any star, an object like Voyager settles toward the temperature of the cosmic microwave background, the faint, ancient afterglow of radiation left over from the early universe. It fills all of space almost perfectly, evenly at a temperature of about 454 F or about 270 C, only a few degrees above absolute zero, the coldest temperature theoretically possible. Once Voyager's power source is fully exhausted and its instruments are cold and silent, it will gradually settle closer to that same near-universal background temperature. It will be an object drifting at a temperature that remains essentially unchanged, no matter where its journey through the galaxy or beyond eventually takes it. Since that cosmic microwave background exists everywhere uniformly, regardless of how close or far Voyager happens to be from any star or galaxy. This uniform cold is itself a kind of stability, ensuring Voyager isn't subject to dramatic temperature swings that might otherwise stress and crack its materials over time. It's also worth acknowledging honestly and directly where our confidence about all of this starts to run out even further than we've already admitted. 1 trillion years is long enough that some genuinely open questions in physics become relevant in ways they simply aren't over more modest timescales. We don't fully understand the ultimate fate of protons, the particles that make up the nucleus of every atom, including the atoms in Voyager's own structure. Some theoretical models in particle physics predict that protons might eventually decay, breaking down into smaller particles, though this has never been observed. Current experimental limits suggest that if proton decay happens at all, it would take place over a timescale of at least 10 to the power of 34 years, a number so large it makes 1 trillion years look almost immediate by comparison if protons are stable indefinitely, which many physicists currently consider likely. Then Voyager's basic atomic structure remains completely secure across the entire 1 trillion year span, with room to spare many times over. There's a related process worth knowing about too, involving the black holes we mentioned earlier. In the 1970s, the physicist Stephen Hawking proposed that black holes aren't perfectly and permanently stable. Instead, he argued they very slowly radiate away energy, over time through a process now called Hawking radiation, gradually losing mass until, in theory, they eventually evaporate entirely. This process is almost inconceivably slow for any black hole of significant size, since the rate of evaporation actually gets slower the more massive the black hole is. That means the largest black holes, including the supermassive ones at the centers of galaxies like our own, and Andromeda, would take a length of time so enormous it makes even 1 trillion years look brief by comparison. At the 1 trillion year mark, then the supermassive black hole sitting at the heart of the merged Milky Way, and Andromeda will still be there. It will be essentially unchanged, continuing to anchor the galaxy's structure the same way it always has. There's an even more distant milestone worth knowing about, called the heat death of the universe, a hypothesized state in which all usable energy has been evenly distributed and no further physical process can occur anywhere. Current estimates place that ultimate endpoint somewhere on the order of 10 to the power of 100 years or beyond, a number so staggeringly larger than 1 trillion that the comparison becomes almost meaningless. At the 1 trillion year mark, we're still in what cosmologists call the stelliferous era, the period during which stars, even if increasingly rare and dim, still exist and still shine, however faintly. It's a universe darkening and quieting, but not yet the true final stillness that lies almost incomprehensibly further out on the timeline. It's worth explaining briefly how astronomers actually arrive at numbers like these, because nobody is simply guessing. The foundation is stellar evolution theory, a body of physics built up over more than a century. It describes how stars of different masses convert hydrogen into helium, and what kind of remnant, white dwarf, neutron star or black hole, each mass range eventually leaves behind. This theory has been tested extensively by observing stars at every stage of their lives. The galaxy conveniently contains stars of every age and mass all at once, giving astronomers a kind of natural laboratory where every stage of stellar evolution can be observed directly. Predicting galactic mergers works differently, relying instead on what are called body simulations. computer models that track the gravitational interactions between enormous numbers of stars. These are checked against actual observations of other galaxies caught in the act of merging elsewhere in the universe. Predicting the accelerating expansion of the universe relies on yet another approach entirely, extrapolating from precise measurements of how fast galaxies at different distances are currently moving away from us. That's combined with theoretical models of dark energy that have consistently matched observational data every time they've been tested. Layer all three of these approaches together, and you get the layered, increasingly uncertain picture we've been describing tonight. It's extremely confident for the first several billion years, reasonably confident through the galactic merger and progressively less precise, though still grounded in real physics as the timescale stretches into the trillions. It helps to ground a number like 1 trillion years against timescales that already feel large from everyday science, since even geological and evolutionary time are dwarfed by comparison. Earth itself is about 4.5 billion years old, a number that already strains most people's intuition. The dinosaurs, which many people think of as almost unimaginably ancient, went extinct about 66 million years ago. That means the entire span of time separating us from the last dinosaurs is only about 168th of Earth's total age. Even the universe itself, at roughly 13.8 billion years old, is only about 3 times older than the Earth. That's a comparison that tends to surprise people who assume the gap between planetary and cosmic timescales must be far larger than it actually is. 1 trillion years is roughly 220 times longer than the entire current age of the Earth. Evolutionary biologists sometimes describe deep time using the metaphor of an outstretched human arm. The entire history of life on Earth spans from shoulder to fingertip, and all of recorded human history is contained within a single pass of a nail file across one fingernail. Using that same metaphor, 1 trillion years would require stretching that arm out roughly 220 times over. It would wrap around the Earth itself many times before you'd finally reach the point. Voyager is expected to still be traveling through space structurally intact, according to everything we currently understand about physics. There's a thought experiment worth including here too, because it captures something important about scale that pure numbers can struggle to convey. Imagine compressing the entire history of the universe from the Big Bang 13.8 billion years ago until today into a single calendar year. On this scale, the Big Bang happens at the very first moment of January 1st. Our sun and solar system don't form until early September. The first simple life on Earth appears sometime in mid to late September. Complex multicellular life doesn't show up until mid-December. Modern humans don't appear until the final minutes of December 31st, and all of recorded human history fits into the last few seconds before midnight. Voyager's launch happens in a fraction of that final second. Now, using that same compressed calendar, 1 trillion years would require roughly 72 additional years beyond that single compressed year stretched out at the same scale. Words like soon, recently, and eventually lose their normal meaning entirely once you're operating on timescales measured in the trillions. An event happening relatively early within this window could still represent a span longer than the entire current age of the universe. Let's bring this back to something a little more grounded, because it's easy to get lost in numbers this large. Think about the room you're sitting in. Right now, think about the building around it, the city around that, the country, the planet, all of it, every structure, every institution, every language spoken by every person alive today exists inside a window of time, so brief compared to Voyager's expected future that the comparison barely functions as a comparison at all. The engineers who designed its power systems and the scientists who selected the sounds and images for its golden record won't see even the first few thousand years of Voyager's continued journey. They certainly won't see the full 1 trillion, and yet the machine itself, indifferent to any of that, simply continues following the same basic physical principles that governed its motion the moment it left Earth's gravity behind. There's a particular irony worth sitting with, because none of this permanence was ever the plan. Both Voyager spacecraft were originally built for a 4-year mission to study Jupiter and Saturn. Engineers had debated exactly how much redundancy to include, knowing every backup component added weight and cost. They chose anyway to build in duplicate systems for critical functions and conservative power budgets, meant to stretch the mission well past its original 4 years. That decision, made purely to protect a modest planetary science mission, is a large part of why Voyager survived long enough to actually leave the solar system in the first place. By extension, it's why Voyager is on track to become one of the most enduring physical objects our species has ever produced. Nearly everything else humanity has ever built remains rooted on Earth, tied to Earth's own fate, whether through the sun's eventual expansion or the far earlier, far more ordinary erosion of wind, water, and geological time, of everything we've made. It's specifically the handful of things we deliberately sent away that stand any real chance of enduring on anything like a cosmic timescale. It's a kind of permanence achieved almost by accident, simply through distance and isolation from everything that normally wears things down. It's worth spending time on what other galaxies, ones we're not merging with, are expected to look like across this same span of time. Voyager's fate is really just one small example of a much broader pattern playing music out everywhere in the universe. Most galaxies exist within larger structures called groups or clusters, gravitationally bound collections that can range from a handful of galaxies to many thousands. Within these bound groups, mergers, similar to the one between the Milky Way and Andromeda, are expected to play out repeatedly over the coming trillions of years, each one consolidating multiple smaller galaxies into fewer, larger ones. Beyond the boundary of each group, though, the accelerating expansion of the universe means neighbouring groups drift apart forever. Their light eventually crosses the cosmological horizon and disappears exactly the way we described happening to every galaxy outside our own local group. The end result, replicated across the entire universe, is an increasingly isolated collection of enormous, quiet, merged galaxies. Each one sits alone in its own patch of an ever-expanding universe with no way of ever detecting or interacting with any of the others again. Whatever galaxy Voyager eventually calls home, whether the merged Milky Way and Andromeda or the emptiness beyond it, it will share this fate with essentially everything else in the observable universe. There's a natural question that comes up once you start thinking this way, and it's probably crossed your mind by now. If Voyager is likely to survive structurally for 1 trillion years or more, and if other civilizations throughout the universe have likely built and launched similar objects, a natural question follows. Are there other golden records, other silent ambassadors drifting through other galaxies right now, sent by civilizations we've never had any way of detecting? We genuinely don't know. And it's important to be honest about that rather than speculate as though we did. We haven't detected any confirmed signals, artifacts, or probes from beyond our own solar system. Despite decades of listening efforts through projects like the Search for Extraterrestrial Intelligence, the absence of a detection doesn't mean the absence of anything out there. Since the galaxy is enormous, and our searching has covered only a tiny fraction of it, any hypothetical alien probe would face exactly the same problem Voyager does, an almost impossibly low chance of ever passing close enough to anything for anyone to actually notice it. If other civilizations have sent out their own version of a golden record, it's statistically most likely still out there right now, unnoticed, following its own version of the same long uneventful path we've been describing for Voyager tonight. It's a humbling thought that the galaxy could in principle already be scattered with quiet ancient artifacts from civilizations long since gone. Each one drifts forever, none of them ever finding each other simply because space is too large and empty for even deliberate messages to reliably find their intended audience. There's one last set of numbers worth holding on to because it brings together the speed, the distance, and the scale we've been describing all night into a single final comparison. Light itself, the fastest thing in the universe. Takes about 23 hours to reach Voyager from Earth at its current distance. Even a signal travelling at the ultimate cosmic speed limit needs the better part of a full day just to cross the gap that currently separates the spacecraft from home. Voyager, moving at roughly 10 km every second, covers a distance in 1 year that would take a commercial airliner more than 60 years of continuous flight to match. And yet, despite having travelled for nearly 50 years at that considerable pace, Voyager has covered barely 1/1400th of the distance to even the nearest star beyond our own Sun. That fact says less about Voyager's speed, which is genuinely remarkable by human standards, and more about just how enormous the true scale of interstellar space actually is. Stretch that same ratio forward to 1 trillion years and Voyager will have completed only a small handful of full orbits around the galactic centre. That's a galaxy so vast that light itself takes roughly 100,000 years just to cross from one edge to the other. Even after outliving its sun, its planet, and its entire species, even after surviving a merger between two entire galaxies, Voyager will still, in a very real sense, have barely begun exploring the single galaxy it now calls home. It will have covered even less of the wider universe that will have long since faded from view around it. There's a specific detail worth understanding about what actually happens to Voyager's orientation once its power is gone, since it changes how we should picture the spacecraft physically moving through the rest of this story. Right now, Voyager maintains a careful, deliberate orientation, its antenna pointed precisely at Earth, using small thrusters that fire tiny controlled bursts to correct any drift. Once power runs out completely, this active control ends and Voyager will begin slowly tumbling. Its orientation will gradually change due to tiny torques, minuscule twisting forces from uneven heating by starlight, subtle gravitational effects, and the slow continued outgassing of trace amounts of material from its own surfaces. This tumbling will be almost imperceptibly slow by any human timescale. But over centuries and then over millennia, Voyager's antenna will point in an ever-changing series of directions, no longer aimed at anything in particular, simply rotating slowly as it drifts. This doesn't affect Voyager's structural durability in any way, but it does mean that even in the hypothetical scenario where some future civilization developed a way to detect Voyager's physical presence from a distance, they'd be looking at an object with no fixed orientation. Its antenna, once purposefully aimed at a specific blue planet, would now simply be pointing wherever the slow accumulated tumble of untold centuries happens to leave it. It's a small, almost poetic detail buried inside an otherwise very technical story. A spacecraft built with such careful, precise attention to orientation and pointing accuracy is music destined to spend the overwhelming majority of its existence slowly, silently tumbling, aimed at nothing at all. It's also worth taking a moment to appreciate just how strange Voyager's communication with Earth actually is even today, because it tells you something about the scale we're dealing with. Voyager's radio transmitter broadcasts with about 23 watts of power, roughly the same as a dim household light bulb. That signal travels more than 15 billion miles before a network of enormous dish antennas on Earth, called the Deep Space Network, manages to detect it. By the time that signal arrives, it has spread out and weakened so dramatically that the antennas on Earth are picking up a whisper measured in a fraction of a billionth of a watt. This tells you something important about the difference between communication and existence. Communication is fragile. It requires power, precision, an intact receiver, and a narrow window of opportunity. Existence, on the other hand, requires almost nothing. A rock doesn't need power to keep existing, and neither does Voyager once its instruments go dark. The fragile part of its story, the part where it talks to us, is nearly over. The durable part, the part where it simply continues to be a physical object in motion, is only just beginning. And it's the part that stretches out across the rest of time. We describe the sun becoming a white dwarf, but it's worth understanding just how strange and long-lived that final stage actually is. It shapes what the entire galaxy will look like by the time Voyager reaches the trillion-year mark. A white dwarf has no fusion happening inside it anymore. No furnace generating new heat, only the leftover thermal energy from its previous life as a star, radiating away slowly into space. Because a white dwarf is so dense and compact, this cooling takes an extraordinarily long time. It's on the order of 1 to 100 quadrillion years before it fades all the way down into what astronomers call a black dwarf, a completely dark, inert remnant with no light output left at all. 1 trillion years is a small fraction of that cooling time, which means our own sun's remnant, sitting quietly out in space long after Earth is gone, will still be glowing faintly at the trillion-year mark, an ember of a star, dim and reddish. It's technically still emitting light, but bearing almost no resemblance to the blazing yellow-white disk we see in our sky today. Red dwarfs tell an even stranger story, and they're arguably the most important detail in this entire timeline, where a star like our Sun burns through its hydrogen supply in about 10 billion years. The smallest red dwarfs burn so slowly and evenly that models suggest they could remain stable and shining for anywhere from 1 trillion to 10 trillion years. That's longer than the current age of the universe, repeated dozens or even hundreds of times over. That means some of them quietly burning in our night sky today, completely unnoticed, will still be shining 1 trillion years into the future. They'll be patiently converting hydrogen into helium at a pace almost meditative next to the massive stars that flare brightly and vanish within a few million years. These red dwarfs will be the last active stars in the universe. By the time they finally exhaust their fuel, tens of trillions of years from now, star formation itself will have ended entirely. The interstellar gas clouds needed to form new stars will have been used up, locked away inside remnants like white dwarfs, neutron stars, and black holes, with no mechanism left to recycle that material back into new stellar nurseries. Let's spend a little more time on rogue planets, too, since they turn out to be a genuinely useful comparison for thinking about what Voyager itself might become. Current estimates based on gravitational microlensing surveys and theoretical models of planetary system evolution suggest that free-floating rogue planets, worlds ejected from their original star systems through gravitational interactions, may actually outnumber planets still orbiting stars within the galaxy. They may do so by a significant margin. These rogue worlds drift silently through interstellar space, unlit by any nearby star. Their surfaces, if they're rocky, locked in permanent absolute darkness and cold. Their temperatures dropping to nearly the background temperature of space itself. There's something worth reflecting on in the parallel between these wandering worlds and Voyager's own likely fate. The very same gravitational forces that eject entire planets from their birth systems, flinging them out into the emptiness between stars, could in principle do the same thing to Voyager. It's a human-made object, experiencing on a much smaller scale the exact same physical process that shapes the fate of entire worlds throughout the galaxy. It's worth contrasting Voyager's fate with what happens to the thousands of other objects humanity has launched into space. Almost none of them are headed anywhere close to this kind of longevity, and the difference comes down entirely to where they were sent. The overwhelming majority of satellites ever launched remain in orbit around Earth itself, some in low orbit, just a few hundred miles up, others much farther out in geostationary orbit, tens of thousands of miles above the surface. Objects in low Earth orbit are still faintly affected by the outermost wisps of Earth's atmosphere. That's an almost imperceptible drag that over years or decades gradually slows them down until they eventually fall back toward Earth and burn up on re-entry. Objects in much higher orbits experience far less of this drag. Some of them, along with countless smaller fragments of space debris left behind by decades of launches, could theoretically remain in Earth orbit for thousands, or in some cases millions of years. Even these long-lived orbital objects, though, remain fundamentally tied to Earth and the solar system. They're subject to the same eventual fate we described earlier, consumed or disrupted when the sun expands into a red giant billions of years from now. Voyager's situation is categorically different precisely because it isn't orbiting anything. It achieved what's called solar system escape velocity, the specific speed required to break completely free of the sun's gravitational pull rather than simply orbiting it at ever greater distances. That single fact is what removes it from the fate awaiting nearly everything else humanity has ever launched. Every satellite still circling Earth, every discarded rocket stage still drifting somewhere in the solar system, remains gravitationally bound to the sun in one way or another. All of it will eventually share in whatever happens to the solar system as a whole. Voyager alone, along with its much smaller number of companion probes headed in similarly outward directions, has actually left that gravitational relationship behind entirely. That's the single biggest reason its story and its future looks so completely different from everything else we've ever sent into space. We touched on the darkening sky earlier, but it's worth understanding the actual mechanism a little more since dark energy is doing something genuinely strange to the universe. In the late 1990s, astronomers studying distant exploding stars called supernovae discovered something unexpected. Distant galaxies weren't just moving away from us. They were moving away, faster and faster over time, an acceleration that shouldn't happen under simple, straightforward gravitational physics. This led to the concept of dark energy, an unexplained property of space itself that appears to be pushing everything apart at an ever-increasing rate. We don't fully understand what dark energy actually is, only that its effects are measurable and consistent across every observation made so far. If this acceleration continues in the way current models predict, then over the coming tens of billions of years, distant galaxies will cross what's called the cosmological event horizon. That's a boundary beyond which the space between us and them is expanding faster than light can cross it. Once a galaxy crosses that horizon, no signal, no light, no information of any kind can ever reach us from it again. It doesn't get destroyed, it simply becomes permanently unreachable, fading first into deep red shift and eventually into complete invisibility. Estimates suggest that within about 100 billion years, nearly every galaxy outside our own local group will have crossed this horizon and disappeared from view for good. It's worth being clear that this darkness isn't the same as emptiness. Matter still exists out there. Dead stars, black holes, drifting gas and dust, cooling white dwarfs, the slow trickle of light from the last remaining red dwarfs. What changes is visibility, not existence. An entire universe still full of structure while becoming permanently undetectable from any single point. Within it, there's also a bit more worth knowing about the magnetic environment Voyager passes through. Since it plays a quiet role in shaping how much radiation damage the spacecraft actually accumulates, the sun generates a vast magnetic bubble called the heliosphere, extending far beyond the orbits of all the planets, deflecting a significant portion of the galactic cosmic rays that would otherwise reach the inner solar system. Once Voyager crossed the helipore in 2012, it left this protective bubble behind entirely. It is now fully exposed to the unfiltered galactic cosmic ray environment, the same high-energy particles responsible for the slow, gradual radiation damage we discussed earlier. The wider galaxy itself has its own large-scale magnetic field far weaker than the Sun's, but extending across enormous distances. It exerts only the faintest influence on the radiation Voyager encounters, nowhere near enough to alter its path, which remains governed almost entirely by gravity rather than magnetism. It's worth returning to the Golden Record one more time because we've talked about its durability, but not about what it was actually designed to do, if it's ever found. That detail says something about how its creators thought about a time scale like this one. Carl Shawn and the committee behind the record etched instructions directly onto its cover in symbolic diagrams rather than written language. They explained how to play it using pulsar positions to indicate the location and approximate launch date of the spacecraft. The choice to use pulsars, rapidly spinning neutron stars that emit extremely regular pulses of radiation, was deliberate because their spin rates change in slow, predictable, well-understood ways over time. That means even a civilization encountering Voyager millions or billions of years from now could theoretically calculate roughly when it was launched simply by measuring how much those pulsar spin rates had shifted since the map was made. At 1 trillion years, this technique likely breaks down entirely, because many of the specific pulsars used as reference points will have gone silent by then, their rotational energy exhausted over such an extreme length of time. The record was never really meant as a message with an expected reply. Carl Sagan himself described it more as a bottle cast into the cosmic ocean, an act of hope rather than a genuine expectation of contact. Given how sparse the galaxy actually is, the odds of Voyager ever passing close enough to a planetary system for anyone to notice it at any point across its journey remain exceptionally small. If Voyager is ever found drifting along its long, slow path through the galaxy or through the emptiness beyond it, the chances are overwhelmingly high that it happens by pure accident. It would be an extraordinarily unlikely coincidence of two trajectories crossing paths in a galaxy filled with far more empty space music than matter. And if that never happens, that isn't a failure. It's simply the most statistically likely outcome for any small object. Released into a galaxy this large, Voyager doesn't need to be found to matter. It already carried out its purpose the moment it left Earth. Now it continues onward, carrying a small fragment of that purpose into a future so distant that purpose, meaning, and even memory eventually stop applying to it in any way we'd recognize. It's worth pausing on just how slow Voyager's journey actually is, compared to what would actually be required to treat interstellar distances as anything other than a multi-trillion-year endeavor. Voyager moves at roughly 38,000 MEPS relative to the Sun, extraordinarily fast by any everyday standard. But a proposed concept called Breakthrough Starshot imagines tiny gram-scale spacecraft attached to lightweight sails, pushed by an enormous array of ground-based lasers to speeds of up to 20% of the speed of light. At that velocity, a probe could reach Proxima Centauri, the nearest star system beyond our own, in roughly 20 years. Compare that to the tens of thousands of years it would take Voyager to cover the same distance at its current speed. The concept remains firmly theoretical, requiring laser infrastructure and material science far beyond what currently exists. But it illustrates the scale of the gap between the speeds we can currently achieve and the speeds that would actually be required to reach another star within a human lifetime. None of these faster concepts address durability the way Voyager's story does, though. A probe travelling at 20% of light speed would need to survive a completely different set of stresses. Extreme heating during acceleration and the risk, music of catastrophic damage from even microscopic dust grains at such enormous velocity are stresses. Voyager drifting slowly and gently through nearly empty space never has to contend with at all. Voyager's slowness in a strange way is exactly what makes its trillion-year survival plausible in the first place. A faster object moving through the same interstellar dust would face a proportionally greater risk of a damaging impact since the energy of any collision increases sharply with speed. Voyager's gentle, patient pace across the galaxy isn't a limitation in this story. It's the entire reason the story is even possible. It's worth understanding a bit more about why star formation actually stops, since that process determines exactly how dark the galaxy will get by the time Voyager reaches the trillion-year mark. Every time a star, particularly a massive one, ends its life in a supernova, it scatters heavier elements forged inside the star through nuclear fusion, or created in the explosion itself out into the surrounding interstellar medium. This is in fact how nearly every element heavier than hydrogen and helium in the universe, including the carbon, oxygen, iron, and calcium that make up planets and living things came to exist in the first place. Each new generation of stars that forms out of this enriched gas contains a slightly higher concentration of these, heavier elements than the generation before it. It's a slow, ongoing process of chemical enrichment that has been playing out across the galaxy for billions of years already. But this process depends entirely on having enough raw hydrogen gas left to form new stars in meaningful numbers, and that raw supply is finite. Once the available hydrogen gas within a galaxy is used up, locked away permanently inside stellar remnants that no longer release it back into the interstellar medium, star formation effectively grinds to a halt. Current models suggest that the merged Milky Way and Andromeda will produce their final generations of new stars sometime within the next few trillion years. This will happen well before the true endpoint of star formation, music, across the wider universe, since more gas-rich galaxies elsewhere may continue forming stars for considerably longer. By the time Voyager reaches the 1 trillion year mark, the merged galaxy it likely calls home in whatever loose sense, a drifting spacecraft can be said. To belong anywhere will already be well past its peak of star formation. It will be coasting on the last remaining reserves of gas, its stellar population increasingly dominated by long-lived, slow, burning red dwarfs, rather than the more varied, more massive, brighter stars that once filled its spiral arms. It's worth being honest about just how quickly precise prediction breaks down when you're tracking a single small object across a timescale like this one, because the uncertainty compounds in a way that's worth understanding rather than glossing over. Even small, seemingly negligible errors in our current measurements of Voyager's exact velocity and position get magnified enormously the further forward in time you project them. This holds true even for the most carefully tracked spacecraft humanity has ever launched, since Voyager's position is currently known with remarkable precision only because we're still actively receiving its signal. Once that signal stops entirely, even this precision starts eroding immediately, since there will be no further data to correct or confirm anything about its ongoing path. A measurement uncertain by a fraction of a percent today becomes an uncertainty of thousands, then millions, then billions of miles. Once you're projecting forward across millions of years, by the time you reach 1 billion years, that same small starting uncertainty has grown into something comparable to the size of the entire solar system. This is a basic feature of how chaotic gravitationally influenced systems behave over long time scales, not a flaw in the mathematics. Small differences in starting conditions lead to increasingly large differences in outcome. The same underlying principle behind why weather becomes essentially unpredictable more than a couple of weeks in advance, just applied here across a vastly longer timescale. This is precisely why scientists can confidently describe the broad shape of Voyager's future. It will likely survive structurally, and it will likely end up somewhere within or beyond the merged Milky Way and Andromeda, while being completely unable to specify anything like precise coordinates for where it will actually be. The physics itself isn't in doubt. It's the practical impossibility of measuring anything with enough precision today to meaningfully project it across 1 trillion years of accumulated small effects that creates the uncertainty. Any honest treatment of this question has to sit with that limitation rather than pretend false precision. It doesn't actually have. It's worth painting a more detailed picture of what it would actually be like if Voyager ever did drift close to one of these dying or dead stars. Since we've mentioned the possibility, but not really described it, given how sparse stars are within a galaxy, even a close pass by cosmic standards would likely mean Voyager passing at a distance of several trillion miles, rather than anything resembling a planetary flyby. There would be no dramatic close encounter of the kind Voyager experienced at Jupiter or Saturn. If it happened to drift near a white dwarf, that faint Earth-sized ember would appear as little more than a dim reddish point of light, its gravity too weak at that distance to meaningfully alter Voyager's course. If it drifted near a black hole instead, at any reasonable distance, the black hole itself would be completely invisible, since it emits no light of its own. The only sign of its presence would be the way it subtly bent the path of anything passing close. Enough, an effect that would only become significant if Voyager passed unusually near, which the sheer emptiness of the galaxy makes extremely unlikely. If it drifted near one of the trillion-year-old red dwarfs instead, still faintly burning after all that time, the encounter would look almost identical to any of the star flybys Voyager already experienced closer to home. It would just be far dimmer, the star itself glowing a deep muted red rather than anything resembling the bright points of light visible in tonight's sky. The far more common experience, if we can even use a word like experience for an object with no instruments left to observe anything. It would simply be more of the same. It would be extended, empty passage through a dark, gently curving path shaped by gravity from very far away. No sudden encounters, no dramatic moments, just the same steady, uneventful drift that has defined the overwhelming majority of Voyager's journey since it first left the solar system. This is worth sitting with, because it's easy to imagine a spacecraft's trillion-year journey as full of near misses and close encounters. The way movies often depict travel through space, the reality is closer to the opposite. The defining feature of Voyager's future isn't event after event, it's silence and distance. That silence and distance is stretched out across a length of time that makes even the rare exceptions. The flybys of Gliese 445 and Sirius feel almost inconsequential against the sheer scale of empty space surrounding them. There's one more detail about the golden record worth knowing, since it shows just how carefully its creators thought about being understood across a timescale like the one we're discussing tonight. Beyond the pulsar map, the record also includes a small sample of pure uranium-238 embedded directly into its cover. Uranium-238 decays at a slow, extremely well understood rate, with a half-life of about 412 billion years, meaning its radioactivity provides a second independent clock built directly into the object itself. Anyone capable of measuring how much of that uranium has decayed relative to its stable decay products could calculate roughly how much time has passed since the record was made. That calculation would be entirely independent of the pulsar map in case one method of dating it turned out to be more useful or more legible than the other to whoever eventually found it. It's a small detail, easy to miss, but it reflects the same underlying philosophy behind almost every choice made about Voyager. Redundancy built in from the start. Nobody expected to need it, but the cost of building it in was so much lower than the cost of being wrong. That same philosophy was quietly applied across power systems, structural materials, and even a message intended for beings who don't exist yet. It turns out to be the single biggest reason Voyager is still capable of teaching us anything at all decades after its launch. There's something worth sitting with here, and it's not really about physics anymore. Every civilization throughout human history has grappled in one way or another with questions of legacy, of what remains after everything else fades, whether through monuments, through written records, through oral traditions passed from one generation to the next. Nearly all of these efforts, however well-intentioned, remain firmly bound to Earth and therefore bound to Earth's own eventual fate. They're destined to be erased one way or another, whether through the slow grinding of geological time or the more dramatic transformation of our sun into a red giant several billion years from now. Voyager represents something categorically different, not because anyone specifically set out to create an object that would outlast civilization itself. It's because the practical requirements of a modest planetary science mission happened to require sending something far enough away that it accidentally achieved a kind of permanence nothing built on Earth could ever hope to match. There's no grand philosophical statement embedded in that fact, no deliberate message about legacy or immortality. It's simply a consequence of physics, of choosing a destination so remote, so empty, so free of the ordinary processes that erode and destroy things. Persistence became the default outcome rather than something that had to be actively engineered or maintained. And maybe that's the most interesting part of this whole story, that the most enduring thing our species has ever created wasn't built with endurance as its primary goal at all. It was simply sent somewhere quiet enough that endurance became inevitable. It's worth imagining for a moment what looking back would actually show if there were anyone or anything aboard Voyager capable of looking back at all. Today, if Voyager's cameras were still active and they were shut off decades ago to save power, turning them toward home would show a pale, faint point of light lost among countless other points of light. That's the same view captured. In the famous photograph taken as Voyager 1 left the solar system, showing Earth as little more than a single pixel suspended in a sunbeam, in a few billion years, that point of light would already be gone. The star it once orbited would have swollen into a red giant and then collapsed into a white dwarf. The planet itself either consumed or left as a scorched, unrecognizable ember. In tens of billions of years, the broader neighborhood of stars we can currently see with the naked eye would have thinned dramatically. Many of the brighter, more massive ones would have already ended their lives, while the galaxy itself began its long, slow merger with Andromeda by 1 trillion years. Looking back toward wherever the solar system once was would show nothing distinguishable at all. No bright point of light, no recognizable arrangement of stars. It would just be the same dim reddish glow of scattered white dwarfs and red dwarfs that fills the rest of the merged galaxy, indistinguishable from any other patch of that same darkened sky. There would be no way, even in principle, to look back and identify the exact point where the journey began, because the very stars and structures that once marked that location will have moved, merged, dimmed, or vanished entirely. Voyager's origin point isn't preserved anywhere in the universe except music within Voyager itself. It's carried forward silently in its golden record and in the simple fact of its continued existence. The only remaining evidence that a specific small, blue planet orbiting a specific ordinary star ever mattered to anyone at all. There's a subtler question worth asking here, too, one that sits somewhere between physics and philosophy about whether an object that has changed this much is still meaningfully the same object at all. Over 1 trillion years, cosmic ray bombardment will have altered Voyager at the atomic level countless times. Individual atoms will have been displaced, bonds broken and reformed, the surface of the spacecraft pitted in, ways too small to see with the naked eye, but real nonetheless. None of this happens all at once, and none of it changes the spacecraft's basic shape or identity in any way a person would recognize as transformation. It's the same way a mountain slowly eroded by wind and rain over millions of years is still recognizably the same mountain at every point along that process, even though not one particle of it may remain unchanged from where it started. Voyager's continuity across 1 trillion years is less like a single object frozen in time. It's more like a very, very slow river, structurally continuous at every moment, gradually different in its exact composition from what it was before, without ever experiencing anything like a sudden break in that continuity. This is worth mentioning because it's tempting to imagine Voyager arriving at the trillionaire mark as some kind of pristine time capsule, exactly as it was in 1977. And that's not quite right. It arrives instead as something more like a fossil, structurally continuous with its original form, recognizably itself, but it bears the accumulated microscopic marks of an almost incomprehensible amount of time spent drifting through radiation, cold, and the occasional stray grain of interstellar dust. That distinction matters because it's a more honest picture of what durability actually looks like at this scale. Not perfect preservation, but continuity. The same basic shape and structure persisting through change rather than being immune to it entirely. It helps to spend a little more time on just how empty the space between stars actually is, because that emptiness is really the single biggest reason any of tonight's story is possible at all. If you shrank the sun down to the size of a marble, Earth would sit about a foot away, itself smaller than a grain of sand. Neptune, the most distant major planet, would sit roughly the length of a football field away from that marble. On that same shrunken scale, the nearest star beyond our own sun would sit, thousands of miles away, a distance that makes even the vast gulf between planets within our own solar system look crowded and close by comparison. On that same marble scale, the entire Milky Way galaxy would stretch across a distance comparable to circling the Earth several times over. The vast majority of that distance would contain nothing solid at all. Just the same thin scattering of gas and dust we described earlier. Voyager, having spent nearly 50 years crossing that first comparatively cramped stretch of our own solar system, has only just begun crossing the truly vast emptiness that separates stars' music from one another. This is part of why collisions remain so unlikely across the entire span of Voyager's journey, no matter how long that journey stretches on. It isn't that space contains no matter at all. It's that whatever matter does exist is spread across distances so enormous that any two objects, even objects moving for 1 trillion years, are statistically very unlikely to ever occupy the same small volume of space at the same moment. The galaxy looks dense and crowded in photographs, thousands of points of light packed into a single frame. But that density is an illusion created by looking at a three-dimensional structure compressed into a flat image. In reality, the distances separating those points of light are so large that the galaxy, for an object actually moving through it, feels less like a crowded room. It feels more like a nearly empty warehouse with a handful of dim light bulbs scattered somewhere inside. Most of them so far apart you could spend a human lifetime walking between any two of them and never get noticeably closer to either. It's worth thinking through what it would actually take for anyone to find Voyager at some point along this journey, since we've discussed the odds being low without spelling out exactly why. Voyager itself is small, roughly the size of a car, and it emits no light of its own once its power runs out. Detecting an object like that from any meaningful distance would require an extraordinarily powerful telescope pointed at exactly the right patch of sky at exactly the right time. Or more plausibly, it would require a direct physical encounter, something passing close enough to notice it by chance. Even reflected sunlight, the way we sometimes spot satellites glinting in Earth's own sky, wouldn't help much once Voyager is far from any star bright enough to illuminate it that way. That leaves it essentially invisible to any method of detection that doesn't involve passing extremely close by. Given that the volume of space Voyager will pass through over 1 trillion years is almost incomprehensibly larger than the volume any searcher could realistically scan in detail. The odds of a deliberate detection remain remote. This is true even for a hypothetical civilization actively searching, let alone one that has no reason to expect anything is out there to look for in the first place. This is worth remembering. Any time the golden record comes up, because it's tempting to picture it as a message waiting to be received, almost like a letter sitting in a mailbox. The more accurate image is closer to a note sealed in a bottle and dropped into an ocean so vast that the nearest shore might be millions of light years away. There's no current reliably carrying it toward any particular destination at all. That doesn't make the gesture behind it any less meaningful. It just means the meaning has to come from the act, music itself, from the decision to try, rather than from any realistic expectation of an answer. Voyager isn't entirely alone in this particular kind of drifting. It's one of only a handful of objects our entire species has ever managed to send far enough to matter on a timescale like this one. The Pioneer 10 and 11 spacecraft, launched slightly before Voyager, are also headed out of the solar system on similar outbound trajectories. Though both lost contact with Earth decades ago, their power sources having run out long before Voyager's, structurally, they should persist for similarly enormous stretches of time. Silent and unreachable, each carries its own smaller, simpler message, a plaque rather than a full record. Similarly resistant to the slow decay processes that affect objects in interstellar space. New Horizons conducted the first close flyby of Pluto before continuing onward into the Kuiper Belt and eventually toward interstellar space itself. It will likely share a similar long-term fate, another small human-made object destined to outlast the civilization that built it by a truly staggering margin. None of these. Other probes carry a message as extensive as Voyager's golden record, but all of them share the same basic physical situation. Small, quiet objects that have crossed the same threshold Voyager crossed, leaving behind the crowded active part of the solar system for the emptier, more permanent drift beyond it. If you could somehow map all of these objects across the galaxy 1 trillion years from now, they would likely still be spread out in roughly the same directions they were originally launched toward. Each one would be following its own slow, mostly straight path, none of them aware of the others, none of them ever likely to cross paths again. It's a strange kind of company. 4 or 5 small silent objects scattered across an entire galaxy, launched within a few years of each other by the same species. They're drifting for the same impossibly long stretch of time, without any way of ever confirming that the others are still out there too. There's a deeper physical principle worth touching on here too, since it quietly governs everything we've described tonight, something physicists call entropy. Entropy is roughly speaking a measure of disorder, and one of the most fundamental laws of physics states that the total entropy of an isolated system tends to increase over time, never decrease. This is why heat flows from hot objects to cold ones, and never the other way on its own. It's also why a dropped glass shatters into disorder, but a shattered glass never spontaneously reassembles itself. And it's why every one of the processes we've described tonight, a star's fuel exhausting itself, a black hole's information slowly leaking away as radiation, a golden record structure being nudged one atom at a time by cosmic rays, all move in the same fundamental direction. Even the heat death of the universe we mentioned earlier is really just entropy's endpoint. The moment everything has finally spread out and evened into a state with no more usable differences left to drive any further change. Voyager's slow physical degradation, the pitting from radiation, the eventual failure of every active system, the gradual settling of its temperature to match the cold background of the universe, is really just entropy doing what entropy always does. It's patiently working to increase disorder wherever it can. What makes Voyager's story remarkable isn't that it resists this process entirely. Nothing can. It's that the specific kind of disorder relevant to destroying it, corrosion, impact, structural collapse, happens to require conditions that simply don't exist in the environment it's traveling through. Entropy still increases atom by atom, cosmic ray by cosmic ray, but it increases slowly enough, and in ways subtle enough that the basic shape and structure of the object can remain intact for a length of time that would destroy almost anything left on the surface of a planet many, many times over. In a sense, Voyager isn't defying the laws of physics at all. It's simply experiencing them in an unusually gentle, unusually patient corner of the universe. The arrow of time still points the same direction it does everywhere else, but that arrow happens to move forward at a pace slow enough for a small human-made object to survive it for a very, very long while. There's a final comparison worth making before we bring all of this together, because it puts the entire scale of tonight's story into a single simple frame. Everything that has ever happened on Earth, every civilization, every war, every invention, every person who has ever lived unfolded within a window of time measured in thousands of years at most. That's a blink against the 4.5 billion year age of the planet itself. Earth's entire history in turn is a small fraction of the roughly 13.8 billion year age of the universe, and the universe's entire history so far. Every galaxy formed, every star born and died, every structure that has ever existed is itself only a small fraction of the 1 trillion years we've spent tonight trying to comprehend. That fraction is less than 2%. Nest all of those numbers inside each other, and Voyager's expected future ends up sitting us at the very outer edge of the frame, dwarfing every other span we've used tonight to try to make sense of it. Voyager is expected to persist through nearly the entirety of that vastly larger span, not as an active functioning machine, but as a simple physical fact, a small collection of aluminum, gold, and plutonium residue continuing to exist because nothing in its path has yet given it a reason to stop. That's really the whole answer to tonight's question. Stripped down to its simplest form, Voyager will be wherever gravity, chance, and the slow unfolding of galactic history happen to carry it. It will still, in some recognizable sense, be Voyager when it gets there, not because it was built to defy time, but because the particular stretch of universe it's travelling through has so little capacity to erase anything at all. It's worth holding on to one more comparison before we bring this to a close, because it captures something about scale that's easy to lose amid all the numbers we've covered tonight. Right now, Voyager is moving roughly 10 miles every second, a pace that would circle Earth in about 40 minutes if it was somehow looping around our planet instead of heading away from it. That's more than 60 times faster than a commercial airliner, and it's still nowhere near fast enough to make interstellar distances feel small in any meaningful way. Over the course of a single human lifetime, roughly 80 years, Voyager will cover a distance of around 26 billion miles, more than 280 times the distance between the Sun and Earth. Multiply that lifetime by 10,000, and you begin to approach the kind of distance Voyager will have covered by the time it makes its distant wide pass near Sirius, hundreds of thousands of years from now. Multiply it by a number so large it stops feeling like multiplication at all, and you arrive at the trillion-year mark. That's a stretch of time during which Voyager will have circled the galactic centre only a small handful of times. Its motion is so slow relative to the sheer scale of the galaxy that even after all that time, it will barely have completed a few laps. Those laps would circle a structure so vast that light itself takes roughly 100,000 years just to cross it from one side to the other. That's the strange, humbling truth sitting underneath everything we've discussed tonight. Even after 1 trillion years, even after outliving its sun, its planet, and its entire species, Voyager will still, in a very real sense, have barely begun exploring the galaxy it now calls home. It's worth returning briefly to the plutonium that once powered Voyager, since its fate over this same span of time is oddly poetic in its own right. Plutonium-238 decays into uranium-234, which itself is radioactive and continues decaying further. It's part of a long chain of transformations that eventually ends after many further steps in a stable, non-reactive form of lead. This entire decay chain unfolds over a length of time far shorter than 1 trillion years. By the time Voyager reaches the point we've spent tonight describing, the plutonium that once kept its instruments alive will have long since finished transforming into inert ordinary metal, indistinguishable atom for atom, from lead found naturally anywhere else in the universe. The very fuel that once let Voyager speak to Earth will have quietly become inert long before the spacecraft itself stops existing. That's one more small transformation completed and finished within the opening fraction of this story, while the object it once powered continues on regardless, indifferent to what its own power source has become. There's a strange symmetry in that. The part of Voyager built to actively do something, to generate power, to enable communication, finishes its transformation and falls permanently silent within a relatively short stretch of this timeline. The part of Voyager built to simply exist, its frame, its structure, its golden record, continues on for the entire remaining span, largely unbothered by what's happened to everything that once made it active. It's a strange kind of aging, backward from how we usually think about it. The part of Voyager that felt most alive, its instruments, its power, its voice, is also the part that goes quiet soonest. Its most inert, unremarkable components, plain metal and gold plating, turn out to be the part best equipped to outlast everything else by an almost unimaginable margin. Maybe that's worth remembering the next time something ends sooner than we'd like, whether it's a mission, a signal, or anything else built to actively do something for a while. The quiet structural remainders left behind often has a longer story left to tell than the active visible part ever did. So let's return one final time to that image because it says everything the numbers were building toward 1 trillion years from now. The sun that once warmed a small blue planet is gone. Its material has been recycled into a cooling ember of a white dwarf drifting through a galaxy that no longer resembles the Milky Way we know today in any way we'd recognize. Earth, if any trace of it survives at all, bears no resemblance to the world that gave rise to the beings who built Voyager in the first place. The Milky Way and Andromeda, once separate galaxies separated by 2.5 million light-years of empty space, have long since merged, settled, and grown quiet. Their combined store of star-forming gas is mostly spent, their remaining light coming from a dwindling population of the slowest, most patient stars in the universe. Beyond the edges of that merged galaxy, the sky shows nothing. No other galaxies, no distant light. No evidence that an entire universe full of billions of other galaxies ever existed at all. From the perspective of anyone or anything standing at that particular point in space and time, and somewhere within, or perhaps well beyond, the boundaries of that quiet, darkened galaxy, a small human-made object continues moving. Its instruments have been silent for the vast, overwhelming majority of its existence, and its golden record still faintly catches whatever dim light happens to reach it, not toward a destination, not away from a threat, simply continuing the way it has continued since a small team of scientists and engineers in 1977 watched a rocket lift off from the coast of Florida. It carries a message meant for no one in particular and everyone who might ever exist at the same time. Thank you for joining me tonight on this journey into a future so distant it barely fits inside human comprehension. If this exploration of Voyager's impossibly long road ahead fascinated you as much as it fascinated me, please take a moment to like this video and subscribe to the channel. It genuinely helps this channel keep making content like this. And the next time you think about how far away tomorrow feels, remember something out past the edge of the solar system. A small machine built by hands that no longer exist is still moving, still carrying its golden record into a darkness that will outlast everything we've ever known. Good night.